Swayam Prabha. Digital India. Educated India.
Welcome. So we have now reached for the module 9, where we will basically discuss the finite element method for two-dimensional elasticity problem. And not only that, in this module we will not solve any problem, rather this module is for formulation, and the next module will try to solve some problem. And this module, so for this lecture what I have planned is this 2D elasticity theory I will just briefly discuss, and then how the weak formulation comes into picture for finite element formulation, that I will describe. Now to start with, so first two-dimensional elasticity, where basically 2D elasticity. So in this elasticity mostly you all know, but I will just briefly introduce it so that you understand this thing clearly. So before that, what kind of problem will be attacking in this module? So the knowledge of this module will help you to solve this kind of problem. For instance, we know in two-dimensional elasticity there are basically so if I just draw an arbitrary body, and this body, if V is the volume, then two-dimensional this V volume I can write it as omega cross this is half of h to minus half of h. Okay, that is the thickness h. So that is, this is equivalent to omega into h. That is, there is a thickness in the body. So this thickness you can consider it like this. Okay, so this is the thickness in the body. Now basically we are considering the mid plane of the body, that is in the thickness direction, it is the mid plane, so 0. So essentially the thickness effect where we can neglect, then we can basically form a two-dimensional elasticity problem. So if I just draw the coordinate system associated with this body, so this is an x direction, we will also call it one direction, and there is a z direction which is essentially in this direction. So it's a planar body or plane elasticity, sometimes it is called plane elasticity. So what are the problems that we'll be trying to solve is something like this, that problem of, suppose I wanted to solve a two-dimensional beam problem. For instance, if there is a cantilever beam, then this beam we have solved for one-dimensional thing. So this is my a beam which is essentially a two-dimensional problem. So this beam we can discretize with finite element. For instance, I can discretize with four-noded element, four-noded quadrilateral element, or we can discretize with the triangular element. For instance, the both of the element you have studied by now. Now so something like this. So this kind of problem you can solve, or we will solve some. So this beam may be loaded with some axial force, or there is some this kind of force. So any kind of force is applicable. So essentially, what is the difference from the one-dimensional problem is that we are considering a two-dimensional problem. So our degrees of freedom essentially is u as well as v. So d of degrees of freedom is essentially u and v. So u is x displacement, y is v displacement. So now it's a vector formulation. Till now we have studied the scalar formulation. So probably you have solved the torsion problem also, which is a scalar field, that torsion function. So stress function basically. So that's a scalar field problem. So now this is a vector field problem. So this is one kind of problem that we'll solve. So for instance, another problem is that that suppose you want to do a axial testing of this kind of bar that some of you have probably solved this kind of. This is a axial testing problem where you will observe stress concentration. Here also you will solve some stress concentration problem. Means we can discretize it with finite element. So we can discretize in several ways. So I am just showing one of the way. So this is how we can discretize. So this kind of problems essentially we will attempt. So now another so this type of problems we know that is plane stress problem. So another kind of problem which is plane strain problem. For instance, if you want to solve a dam problem where the thickness direction is very large or highly thick problem, so something like this. So this is just something like this. So this is axial force sometimes we can apply, or some horizontal force we can also apply. So this kind of, so water pressure may also be there. So this kind of problem also we can solve. So that means this problem is essentially is thickness direction is infinite large. So this kind of problem also known as the plane strain problem. So the basic assumption for 2D elasticity or the plane stress and plane strain problem, we all know that in case of a plane strain, a plane stress problem, what is the criteria? That is your sigma x z and sigma y z and sigma z is essentially 0. So this is the, or the sigma z z is essentially 0. So this is the assumption for plane stress. So all other stresses are non-zero. So similarly, there is no assumption on the strains. So strains, what will happen is that strains will be 0, but it is not necessary that epsilon z z is 0. So that's why it is called plane stress. Now similarly, in the case of a plane strain, so plane strain problem where we say that epsilon xz or gamma xz, whatever you call that epsilon yz and epsilon zz is 0. So all other strains are non-zero. So that's why the plane strain will create a third direction stress. So that's why the infinite thickness or the thickness which is large essentially, or the thick problem, we can approximate three-dimensional problem, we can essentially approximate with the plane strain assumption. So this plane strain assumption sigma zz is not 0. So this is the basics we need before we jump into the weak form. And now we all know the governing equation of any three-dimensional body. For instance, if a three-dimensional body, if I considered, then the governing equation of the three-dimensional body is del dot sigma plus F is essentially 0. So here sigma is a tensor, two-dimensional means three-dimensional stress tensor. Which is having, if you represent in matrix form, this is 3 by 3 matrix, and we all know that stress tensor is symmetric because of the angular momentum balance. And now this is the body force, and now if you want to consider the dynamic effect, then you also introduce rho u double dot. That is, the u is a vector here, obviously. U is a u contains u, v and w. So this is the three-dimensional body. So this is applicable in the total volume V. And then so let me put it like this. So this is a two-dimensional stress tensor. Now this is a vector, this is a vector. So divergence of sigma will certainly the quantity, and Fx or Fy or Fz is the body force term. Now this is in V, and then you will have this quantity, that is the traction force, the applied traction, which is, we know that sigma dot n, that is n is the unit normal. So now this is again a stress tensor, so dot product of that will create a vector. So n is also a vector, so three-dimensional normal vector. Now this is actually the applied traction on the traction boundary, or the prescribed traction. So this is in traction boundary, that is lambda t, and then you will have the u vector known for some position, that is the Dirichlet boundary or displacement boundary. So that's the basic thing. So if I consider the 3D thing, so if I divide this is traction and displacement boundary. So this is my displacement boundary, say, and this is my traction boundary. So there is some forces here applied in some parts of the traction boundary. So here the traction is 0, so that is T bar is 0. So this is essentially T bar, and this is displacement boundary. So this displacement boundary I can choose. So this is an abstract form for 3D. Now if you submit this is displacement boundary. So now if you use this plane stress and plane strain assumption to this equation, so this equation finally leads to a simplified version of the two-dimensional elasticity problem. So let me now write this thing. For instance, this 2D elasticity, what will be the governing equation? So 2D governing equation, what will be the our governing equation? That is your partial derivative of del sigma xx by del x plus del sigma xy by del y plus fx plus rho your u double dot. So now the second equation again will have del sigma xy by del x plus del sigma yy by del y plus fy will be your rho v double dot. So this is my basic differential equation, and then the boundary condition again sigma dot n, that is your Tx. Let me define it as Tx. Tx is sigma xx nx plus sigma xy ny. So these are the unit normal components. So Ty sigma xy nx and sigma yy ny. So basically what I mean to say by this, that if I look for the 2D body, so there is a normal, this is my normal vector. So this normal vector has two components, nx and ny. So now this is along x-axis, it is projection is nx, and this is ny. So this is what is this. So now the displacement again, u is prescribed. So this is prescribed at Tx bar and Ty bar. So bar quantities are prescribed quantities, and u is u bar So and V is V bar. So that is also a prescribed quantity in lambda u, and this is prescribed in lambda t, and this is over the omega is the two-dimensional body, including that omega cross h, that is your h is the thickness of the body. So now this differential equation, our main job is to construct its weak form. But before we construct the weak form, we need to know what is the constitutive equation, because sigma is a stress quantity. So if I assume that first let us define the strain quantities. So we all know the strains, that is, which is, for instance, the strain quantities required for us is that epsilon xx, that is, we know del u del x, and epsilon yy, we all know del u del v del y, and epsilon xy or 2 epsilon xy, that is your gamma xy, that is your shear strain. So that is equals to del u del x plus, sorry, del u del y plus del u del y plus del v del x, right. So this is my strain quantity. Then comes into constitutive relation. So if you assume plane stress, there will be constitutive relation. There will be plane strain, there will be constitutive relation. If you assume the material is isotropic, then there is a different constitutive relation. If you assume the material is orthotropic, then there is a different constitutive relation. So essentially I will I'll do the weak form for a general constitutive relation for an orthotropic material. And then if you substitute the isotropic assumption into it, then we know what are the materials values. So orthotropic means there is two direction, the properties are different. So essentially the stress strain relation, I am just writing it in matrix form: sigma yy, sigma xy. So that is equals to C11, say C11, C12, 0, C12, C22, 0, and 0, 0, C66. Now this is multiplied by the strains. So linear elastic Hooke's laws. So epsilon xx, epsilon yy, and 2 epsilon xy. So now this is my linear elastic Hooke's law. Now here what I have assumed that suppose this is my material. So consider this is my body and this is my material. So here what I assume that this is my material axis. So this is my one axis, this is my two axis. So now this kind of material, suppose there is a composite. So composites fibers are like this. So something like this. So here our material axis of the material, or the axis of the material, coincides with the structural axis. So that means this is my structure, that is my x direction, and this is my y direction. So it is possible that our material orientation is something like this. For instance, something like this, that is your something like this, our material axis. So fibers are aligned along some 45-degree angle. So now this is my material axis. So this is my one axis and this is my two axis. So for instance, this is my one axis, this is my two axis. So now here material axis is not same as the structural axis or the body axis. So when the material axis is oriented about the body axis, then we have to do the transformation of this constitutive matrix. So that we know from, so if this is the angle of theta, then we know how to transfer this quantity to the material axis to the essentially structural axis. So this constitutive matrix, this equation, if I write it in notation, that is sigma is essentially your C matrix, and then this is my epsilon matrix. So now this C matrix for this theta has to be modified and stresses has to be. So this is the relation in the 1-2 relation, 1-2 case. That is the material axis. Now you have to transform this relation to the structural axis and then use that. So here we will not go to this complicated thing, that is when the material axis is not oriented for the structural axis. We can do that very easily by just using the transformation. So that's the thing. Now if I assume that our material axis and my structural axis is same, then my C11 so if I consider a simple orthotropic material, then we'll have 4 material constant for 2D bodies. So 2D plane bodies. So that is in case of a 3D it's 9 obviously. So E1, E2 and nu 1 2 and then G1 2. So now these are material constants. So material constants. So now this is there is a relation that is you know probably, that is nu 1 2, that E2 is essentially nu 2 1 E1. So this is my this is the relation it follows. So now C11, if I do it for plane stress, so you also know that plane stress and plane strain constitutive relations are different. So now in case of a plane stress problem, C11 is looking like this, that is E1 into 1 minus nu 1 2 nu 2 1. So you see nu 2 1 is not an independent material constant because it is related to the other 3 independent material constants. So this is just for simplicity in writing. So this is C22 is similarly E2 into 1 minus nu 1 2 and nu 2 1. So C12 again we can write, that is nu 1 2 E2 sorry, nu 1 2 C11 C22 or nu 2 1 C11. So this is how we know this, and this is C66 is essentially the shear modulus, that is 1 2. Now if this is an isotropic material, so this is for orthotropic material. Now if this is an isotropic material, then obviously E1 equals to E2 equals to E, we can substitute, and the Poisson's ratios we know, that is nu 1 2 is actually nu, and that is equals to nu 2 1. So now this shear modulus we also know, that is E into 2 into 1 plus nu. So that's the plane stress case. Now in case of a plane strain, again I'm just doing this for your just understanding, that is C11 will be E1 into 1 minus nu 1 2 by 1 minus nu 1 2 minus 2 nu 1 2 nu 2 1. So this is the plane stress quantity that constitute matrix C11 will have this. Now this is you see it is different than the plane stress. Now similarly C22 is essentially E2 into 1 minus nu 1 2 nu 2 1 divided by 1 minus nu 1 2 minus 2 nu 1 2 nu 2 1 into 1 plus nu 1 2. So and C12 is nu 1 2 E2. This proof you can see for any books on composites, you can see this proof. So 1 minus nu 1 2 minus 2 nu 1 2 nu 2 1, and C66 is your G12. So this is for plane strain. Now if you substitute isotropic case, that is this case, then you will get the isotropic plane stress. plane strain constitutive equation. So the essential quantity we have defined now. We have stress strain relationship, we have kinematics, that is displacements and strains. Displacements are two dimensional here, so displacement is a vector now, so that is u and v. Now so 2 degree of freedom per node problem. Now so if I substitute this kinematic, this constitutive equation to this equation, then our governing equation looks like something this. So let me just write it. For instance, sigma xx, we can write C11 epsilon xx plus C12 epsilon yy, that we can write C11 del u del x plus C12 del v del y. So sigma xy, if I write, then this is nothing but C66 2 epsilon xy, so 2 epsilon xy. So epsilon xy we know, so C2 will cancel, so that is equals to del u del y plus del v del x. So that is my sigma xx, and sigma yy similarly C12 epsilon xx plus C22 epsilon yy, that is equals to C12 del u del x plus C22 del v del y. So now if I substitute this quantity in this 2D equation, that is del sigma xx del x plus del sigma xy del y plus f of x equals to rho u double dot, and del sigma xx xy del y plus del sigma yy del y plus fy equals to rho v double dot. So this, if I substitute, then essentially what we are doing here, we are just using the constitutive relation. So this is a first order equation. If you substitute the constitutive equation, this will lead to a second order equation, because it is second order equation in terms of displacement, because displacement strains are the first order derivative of the displacement. So if you substitute it, this will become a second order equation. Now this second order equation, if you want to do the weak form, we know how to do it for one dimensional case, right? So now this equation leads to simple thing. I will just write it little bit proper way, that is the minus del x into your this equation, that is C11 del u del x plus C12 del v del x del v del y minus del y, that is sigma xy. So C66 del u del x del u del y plus del v del x. So this is my these two terms. Then that is equals to minus your fx minus rho u double dot. So rho u double dot means essentially the time derivative. So rho del 2 u by del t square. So essentially u is function of three variables, u comma x and x, y and t. Similarly, v is a function of v of x, y and t. So earlier it was function of x only. So similarly, the second equation that we can also write, that is del y del x into your C66 del u del y plus del v del x minus del y into your this equation, that is C12 del u del x plus C22 del v del y. This will be your fy minus rho del 2u del t square. So del 2v del t square. So that's the inertia term. So if there is a damping, then you have to have a damping term too. So now if you know the probably you have studied the principle of virtual displacement. So we can construct this from the virtual, the weak form can be constructed from the variation principles or the principle of virtual displacement. So that's from the energy point of view, we can also construct that we have studied already for the one-dimensional problem. So if I just write it for the virtual displacement thing, then if that is the integral v is my domain, and then we can write it very easily something like that, sigma ij del epsilon ij plus your rho u double dot I delta ui. So these are delta variable for displacement. Now delta variable of the displacement is this is delta variation of the strains. So that is equals to dv. So this is over the body, and then the body force term. So that body force term is your Fi. So you know there is a integration by parts, so that's why it is like this. So Fi is I is x, y, and x and y here. So that is your delta ui. So that is the similar way that we did it for the two-dimensional problem. So integration is over the volume. Now there is a term that will come into the boundary term that will come, that is the traction boundary condition or the Newman boundary condition. Because of that which will come, so that will be your over the surface, that is your surface S, say. So that will be actually your T bar I delta ui. So that is my delta S ds over the surface. So this quantity is actually 0. So here the variation is actually the displacement. So the from the variation of the displacement we can carry out the variation of the strain. So that is simple, because you have to just take the derivative. So derivatives and commutative, so you can take out the variation. For instance, we already seen these things. So epsilon xs is del u del x. So simply delta epsilon xx is delta of del u del x. So we can take this as ddx of delta dodo x of delta u. So essentially this is nothing but delta of that is the strains. So delta of u x is the derivative of the that means this I can write like this, that is delta x of del u. So this is the property of commutativeness of the delta operator. So these things we have studied already. So this thing is the weak form. Now if this is general 3D weak form. Now if I had to 3D variational statement. Okay, now if I wanted to modify it for 2D, then integral, so my domain is now V is omega cross H. H is my thickness. So it will be the volume integral will be a surface integral here, and this will be surface integral here, and then this will be your line integral. So now this weak form for 2D, this variational statement for 2D will be your omega over omega. So thickness will be multiplied H, and then this will be sigma ij delta epsilon ij plus rho ui delta ui, then dx dy. So now my domain is two-dimensional domain in xy plane. So now this is again omega, then fi, or it is better to represent it as d omega because I am using ij. So d omega. So fi delta ui d omega Now this is again, so this is again the traction. So traction will be over gamma. So gamma is a line integral. So the boundary of a surface is essentially line. So now Ti bar delta ui d gamma. So that's for 2D. Now this is one way of doing it. Another way of doing it, just to use, so these are the variations of the delta, is a variations of the displacement. Now another way of doing it by weighted residual method or Rayleigh-Ridge method that we studied. So in that method, what we do, we multiply weight functions W1 and W2 here, because there are two differential equations essentially. So similarly, we multiply weight functions W1 and W2, the two different weight functions. So we also know that weight functions has to satisfy some conditions. So all those whatever you have studied in the one-dimensional case, it is totally applicable here. So now again, if I so integral statement is this, that you multiply with this equation with W1 and weighted integral statement, make it to 0, and then do the integration by parts. So if I just do that integration by parts, so essentially multiplying the governing equation with the W1, so the first equation will look like, so basically the weak form will look like this. So now that's why I just rearrange this equation, because if you integrate by parts, then there will be a minus term will come, so minus will cancel. So essentially it will look like this, that is over omega, that is your del W1 del x, and then that is this quantity is transferred to the W. Now W, the weight function again is a function of xy. So weight function is now your domain is not one-dimensional domain, your domain is two-dimensional domain. So that's why weight functions has to be function of xy. So now this will look like this, that is C11 del u del x plus C12 del v del y. Now we can use dx dy. So this omega is a this thing, your two-dimensional domain, and then the second term again will have this plus integral over omega del w1 by del y. So now this will have C66 del u del y plus del v del x. So this will have the second term, and then the third term, that is your this quantity will be, so by doing this integration parts by parts, we will have the boundary term also. So this boundary term I will write later. So now this I can write as minus integral f x into w1 dx dy, or yes, here there will be dx dy, then dx dy. This is also a surface integral. Now this quantity will also have the inertia quantity, that will also have the this effect. So that is equals to integral over surface, that will have your rho can be a function of x. So rho w1 into del 2 u del t square. So that is dx dy. So this is the volume quantity, and then we will have again the boundary term that is automatically popping up from the integration by parts. So what will happen to the boundary term? So now the boundary term will be so again minus, so now this will be over gamma. So here again this quantity will be multiplied with the h always multiplied with the h, because we have converted it with the 3D to 2D problem. Now omega is my 2D domain. So again the boundary term will also have the 2D domain. So here the h will be there. Now here we'll have this quantity. So this is my first boundary term. So W1 into your del u del x plus C11 del u del x, C11 del u del x plus C12 del v del y into nx. Your if you remember that our boundary condition, that is your this condition. So this condition will be there. So that is sigma xx. So now this condition into a nx. So now plus your W1 into your this quantity, that is your C66 del u del y into plus C66 del v del x into ny. So these are the components. Now this is integrated over del L or del S, or this is essentially the line integral. So essentially line integral here I will represent as d small s. So that is your, if this is the 2D domain, so this thing is my s. So remember this is the line integral. So in case of finite element formulation, the force vector will have the implication of this. So this will be little different here. So we'll discuss that in later class. So this equation will be essentially 0. So this is the first equation. Now similarly the second equation we can also write from the second this thing. So here again if I write the second equation, we have to multiply with h. So omega, that is del omega 2 del y or del x. The first term is del x. So now C66 del u by del y plus del v by del x into your dx dy. So that is my surface, that is first term. Then again h multiply by del omega 2 by del y into your C12 del u del x plus C22 del v del y dx dy. And similarly we will have fy term, that is also over omega, that is your w2 dx dy plus integral rho omega 2 del 2v by del t square dx dy, and then the boundary term again. So the boundary term will pop up because of the integration by parts that we have seen earlier. So now this is w1, now we'll have w2, now we'll have C22, that is your del u del x plus del v del u del y and del v del x, and then this will be multiplied with nx plus your w2 multiplied by your this quantity, that is C12 del u del x plus C22 del v del y. So now this will be ny. So now this again is the small surface S. So this is my boundary term. So now this is the essentially the boundary term. Now this is the total weak form. This is the first weak form and this is the second weak form. Now here these two weak forms is essentially is a bilinear form. So now the bilinear form is a vector quantity. So if I combine this thing, so this is the this part is my bilinear form. So if you look carefully, so this is my bilinear form. Now and this is the linear form. So here also this will also come into the bilinear form. So this is the this will come into linear form, and this quantity, obviously we know this quantity is prescribed quantity, so we know what is it. So this is nothing but this plus this is Tx and Ty, so we can substitute that. So here I stop today. So in the next class we'll just learn the how to matricize or the matrix expression of this equation, so that we can do finite element analysis with ease. So here I stop today. Thank you.